Hey guys, your boy Chill here. Welcome back to Advanced C++ Tutorial 6, Part 2. In Part 1, I introduced you guys to shared pointer, gave you the basics of how to use it. In this video, we're going to do a deep dive. We're going to look at the implementation of shared pointer, and we're going to look at the shared pointer ecosystem, all the utility functions that surround it. Now, before we dig into the guts of shared pointer, I've got to introduce to you guys a different pointer type, weak pointer. And you might be saying, Chili, why are you throwing another pointer type at us? This tutorial is supposed to be about shared pointer. Well, here's the thing about weak pointer. Weak pointer isn't its own separate type. It exists as a supplement to shared pointer. It's wholly inside the shared pointer ecosystem. You never use weak pointer without shared pointer. So, everybody knows unique pointer. Everybody knows shared pointer. Not a lot of people are really clear on weak pointer, and that's because it's not its own thing. It's only used in special situations to support the usage of shared pointer. Now, to understand the big picture of shared pointer, you really have to also understand weak pointer, how to use it, and why it is necessary. So I'm going to hit you guys with a little bit of a scenario here. So we're going to have two class types, alpha and beta, and they're both going to contain pointers to link to the other type. So a beta will have a pointer to alpha, and an alpha will have a pointer to beta. And using this, we can set up a bidirectional link between instances of alpha and beta. So if we look at the code here, you see I've added 4 files here, .h and .cpp files for alpha and beta. So if you look at alpha, we see it has a constructor, a destructor. These guys are just to announce and also to take in a string parameter. And then there's a function to speak the name of the instance and to make the linked instance speak its own name. The links are held via shared pointer. And this is important because you want to keep the thing on the other end of the link alive. If the thing on the other end of the link can die at any time, that will create problems. You'll get memory access issues and you'll crash your program. So using a shared pointer for the link here is a good idea. Now, to actually create the link between two objects, we have a free function called link, accepts shared pointer to alpha and beta and links them together. And it has to be a friend of both alpha and beta because it's going to be accessing this private data. If you look at alpha.cpp, it's very simple. Constructor, destructor, simple announcement, speak. Make linked speak will check to see if there is a linked instance. If so, it'll make it speak. If not, it'll just print out a message that there was no linked instance. And the link function, the free function here is simple. And beta.cpp, it's the same deal as alpha. So it's not a very complicated system. Let's take it out for a test drive. So we're going to create shared pointers to an alpha and a beta. And then let's try to call make linked speak on alpha and beta here. So we'll set a breakpoint. So we create our alpha, we create our beta. And if we look at our window here, yep, they were both created. Let's try to make the linked ones speak. And it says there is no linked beta, there is no linked alpha. I should put a new line in there. There we go, I fixed it. All right, so this is working as expected. And then if we step out of this scope here, we should expect, alpha dies and beta dies. Now let's link these two instances together. So we're gonna call link with p alpha and p beta. I'm gonna run it. So now we've linked these two instances together, and when we call make linked speak on alpha, it's going to say linked beta instance says hello from my beta. And we get the same thing when we call pbeta.make linked speak. That's going to cause the alpha to speak. All right, so far so good. And now when we leave this, all our memory should be cleaned up. Oh no, memory has not been cleaned up. What the heck? Well, this was foreseeable. We create an instance of alpha and beta as a shared pointer. So we got p alpha, p beta, then we link them together. Then when we go out of scope, the things that were created in scope, which would be the p alpha and the p beta, these pointers die. They no longer reference these objects, but there is still a reference to alpha, right? It's coming from beta. And there's still a reference to beta. It's coming from alpha. Alpha is keeping beta alive, is keeping alpha alive, is keeping beta alive, and we have just discovered the secret to immortality. Unfortunately, we no longer have any external handles on these objects. They're just floating around now on the heap, keeping each other alive, and we cannot access them, i.e. got a big old memory leak. So clearly this cyclic dependency here is causing a problem. And you might say, Chili, I got you on this one. I can fix the problem. All we got to do, we got to break the cycle. So instead of doing a shared pointer to alpha in beta, we're just going to do a raw pointer. We don't have to change anything in beta.cpp because the semantics are still the same. All we got to do is in the link function, instead of setting p alpha equal to the passed in shared pointer, we want to set it equal to the raw pointer that is held by that shared pointer. So if we build this, you see it runs fine. Let's try to actually run it. So we create, we link, we speak, we destroy. What do we have? Well, it worked. That was easy, right? Okay, problem solved. Just don't have a cycle of shared pointers. Make one of those bad boys a dumb pointer. Well, let's spice things up a little bit now. Let's say after we call p alpha, make linked speak, we are going to free that resource. So we're going to reset the shared pointer. What happens now? Well, create the shared pointers, link up the instances, make the beta speak from alpha, reset alpha, make alpha speak from beta. Oh my God, we just crashed the program. Well, that's not good, is it? And you see, this was also rather foreseeable. We had two smart pointers keeping alpha and beta alive. Alpha keeps beta alive, but beta does not keep alpha alive. Then when we reset this pointer to alpha, all of a sudden nothing is keeping alpha alive. So alpha is also destroyed, and this reference to beta is destroyed, but beta still has one reference to it, so it's alive, but it has a dumb pointer now pointing into empty space. And when we try to access that to do something, we're going to have a bad day. So the solution to this problem, you might have guessed it, is to use a weak pointer. So we can break the cycle by replacing one of the shared pointers with a weak pointer. And the difference between a shared pointer and a weak pointer, well, there's a bunch of differences. The main one is that it will not keep alpha alive. So now when we destroy this, alpha will also be destroyed. And you might say, well, Chili, isn't that the same situation as you had with a dumb pointer? Well, no, because a weak pointer, unlike a dumb pointer, is aware of the entire shared pointer system. So with a weak pointer, you can actually query to see whether there's anything at the end of this weak pointer or whether it's already been destroyed. You can't do that with a dumb pointer. So here's how that looks. Let's go into beta.h and let's replace the alpha pointer here, the dumb pointer, with a std weak pointer. Now this is going to require some changes in the beta code because you can't just use a weak pointer on its own. What you have to do is you have to lock the weak pointer and get a shared pointer, and then you can use that shared pointer. So when you have a weak pointer, you don't know if there's anything at the end of that weak pointer. So let's do auto p shared is equal to p alpha, this is our weak pointer, dot lock. And what lock is going to do is it is going to return a shared pointer. It's going to get a lock on it. So the shared pointer is now going to be keeping that instance alive, which is good because if we're going to be working with it, we want to keep it alive for the duration of what we're going to be doing. So that's what lock is doing. It's getting a shared pointer. It's going to keep that alive until we're done with that shared pointer. The other thing about lock is if the thing is already dead, if there's nothing at the end of our weak pointer, it'll just return an empty shared pointer. And an empty shared pointer in an if statement is going to evaluate to false, and then we're going to get this behavior here. So now we have our p shared. If there was anything at the end of that, we've got a p shared, and we can use that to access the alpha. If nothing was at the end of our weak pointer, we're just going to hit this end of the branch, and nothing bad is going to happen. Now, the final thing we got to fix up here is our link function. And we can revert it back to the previous behavior because you can initialize a weak pointer from a shared pointer, no problem. So this is our weak pointer. We're going to initialize it from the shared pointer. And then whenever we want to access from beta, we lock our weak pointer and then we do our accessing. And then when we leave this, the shared instance will be freed. The reference will be decremented, and we're not going to get this situation where they're both keeping each other alive. So let's try this out here. All right, we create our instances, we link them together. We're going to make beta speak. Beta has spoken. We're going to delete alpha. We're going to try to make alpha speak. We didn't crash. It tells us there is no linked alpha, which is true. And then we leave the scope. And now beta has also been freed. So all resources freed. No dangling pointer issues. Everything is great. This is the reason why weak pointer exists. And of course, there are other usage scenarios for weak pointer. I've just shown you the most basic one here, but I don't want this video to be 3 hours long, so we'll just leave it at that. Now you should understand why weak pointer is a necessary part of the shared pointer ecosystem. Now at this point, you might have a bunch of questions, and that's good. One of the questions you might have is, well, weak pointer, if this is destroyed, what is the weak pointer actually doing to check to see whether there's anything at the other end? If the object is destroyed, there's nothing there. There shouldn't be anything that you could access to check. And what about like use count from the previous video? How does it know how many other smart pointers are accessing this object? What kind of telepathy is involved in that? These are some of the questions you might have. Another question is, what exactly is stored in a shared pointer? Is it just the address of the object here, or is there something else? So I'm going to hit you guys here with a basic explanation of the internals of shared pointer, not specific to any particular library implementation, just a general idea here. There's two cases. We'll start with the general case, and then there's a special optimized case. So you've got a shared pointer, and it's going to manage some kind of resource, typically, allocated on the heap. Now the missing piece of the puzzle here is the thing that implements all this cool machinery, and that is called the control block. The control block is where all this good information is stored. So the control block is going to contain a pointer to the resource, and the control block is also going to store the use count. And your shared pointer is going to have a pointer to the control block. Now, when you copy a shared pointer, what's going to happen is this shared pointer is also going to point to this control block, and the use count is going to be incremented. So that is how this pointer knows when another reference has been added to this resource. It's because they're both not referencing the resource directly, they're both referencing this control block. When a shared pointer is deleted, this use count is decremented, and when the final shared pointer is deleted, the use count is decremented to 0. This shared pointer object sees that the use counter is 0, so it also will destroy the resource, and it will destroy the control block. This is the simplest picture of how shared pointer works. It's also a bit of a lie. So let's rewind things here for a second. Let's add to the equation a weak pointer. All right. Now this weak pointer, as we know, it doesn't keep the object alive. So it doesn't influence the use count. There are 2 use counts. There's only 1 weak pointer to this control block here. So with the old story I just told you, if I delete this guy and I delete this guy, use count goes to 0. This gets deleted. This gets deleted. This has a dangling pointer, and the next time you try to call weakpointer.lock, you're going to crash your program. So obviously, there's more to the story. And that more to the story is that there is a second counter in the control block called the weak count, or whatever you want to call it. Doesn't matter what you call it. What matters is that the control block isn't deleted unless the weak count goes to 0. So I can delete this smart pointer. I can delete this smart pointer. The use count goes to 0. The resource gets freed, but the control block is still alive because the weak count will go to 1. Why? Because there's still a weak pointer that has a handle on this block. And so the control block will remain, and you can call weak pointer.lock, and it will tell you there is no resource. Now the counting here for these 2 counters is a little funky, especially for the weak counter. For the use counter, it's very simple. Use counter is just equal to the number of shared pointers that own this resource. Weak counter is equal to the number of weak pointers that own the resource plus 1 if any shared pointer also owns the resource. So in this scenario, it's going to be 2 because there's one weak pointer and there are some shared pointers. If you add another shared pointer, what do the counts become? Well, the use count goes up to 3, but the weak count stays at 2. You only ever get a plus 1 for any shared pointers. But if you added another weak pointer, call it weak pointer 2, that would increment the weak count, but not the use count because they're weak pointers. You can delete this weak pointer, you can delete this weak pointer. What will the weak count be after that? It's going to be 1. You delete this shared pointer, the weak count stays at 1, the use count goes down to 2. Delete this one, use count goes down to 1. Delete this one, use count goes down to 0. This is freed. Weak count goes down to 0. This is freed. So to summarize, the use count is very simple. It's just equal to the number of shared pointers that own the resource. The weak count is equal to the number of weak pointers that own the resource plus 1 if the number of shared pointers is greater than 0. If the use count reaches 0, you free the resource. If the weak count equals 0, you free the control block. And that, my friends, is how babies are made, or at least how they're shared. One final little detail. The shared pointers and the weak pointer, they contain pointers to the control block, but they also have a pointer directly to the resource, which is nice because that means you don't have to go to the control block every time you want to access the resource. You can just access it directly. So like I said, this is the general case, and this is the case that you get if you construct a shared pointer with its constructor. So if you call its constructor and you pass it a pointer to a resource, the constructor will create the control block and it will set all this up. Now the special case happens if you create your shared pointer with make shared. So with make shared, the function is going to allocate the object itself, the type, and is going to allocate the control block all at once. And because it's doing these two things, it can actually put them both together in the same memory allocation. So it has the use count and the weak count and the t all together in the same block. And then in your shared pointer, your control block pointer is going to point to the beginning of the control block, and your t pointer is going to point to the beginning of your t type. But it's all in the same contiguous memory. It requires only one allocation instead of 2 allocations. It's just more efficient this way. And this is the primary reason why we are told to prefer make shared whenever we can. All right, now I'm going to take a super quick look at the multi-threading and the synchronization behavior of shared pointers. I'm not going to go into super detail about this because, multi-threading is its own topic, but I want you guys just to be aware of the issues a little bit. So let's say we've got 2 threads here. They both have a shared pointer to some resource, and they're both simultaneously trying to destroy that resource. So these shared pointers in thread 1 and thread 2 are concurrently being destroyed at exactly the same time. So what happens? Well, you're going to decrement the use count, possibly the weak count, and if they go down to 0, you're going to deallocate things. All right? So if we break down the process of decrementing, it's going to be, well, both are going to read the value of the count, 2 and 2. Then they're both going to subtract 1 from that value. So they're going to both be 1. They're going to look at it. They're going to say, there's still 1 left. I don't have to destroy it. But they're both going to write a 1 back into here. So the use count goes down to 1, and then these are both gone, and this memory is leaked. It was a simplification, but you get the idea. So in order to prevent this situation from happening, there has to be special synchronization primitives used for the use count and for the weak count to ensure that operations happen in order. What I just showed you there is called a race condition, and it'll prevent that, saying basically instead of both of these doing the operation simultaneously, if they both try to do it simultaneously, one will happen first, and then after that's happened, the second one will happen. And in that case, they can't both load the value 2. One of them is going to decrement it first, and then the second one is going to load the value 1, decrement it, and do its thing. In reality, it's more complicated. It's going to use something called atomic operations, which are faster. But even atomic operations are still slower than accessing memory normally. And that's something to keep in mind. And that's one of the main reasons why in part 1, I told you don't pass your smart pointers around willy-nilly by value, because every time you pass it around by value, you got to make a copy. And when you make a copy, you've got to increment this use count. And when you do that, you've basically got to lock the data. And it's not a super expensive operation, but it does have a cost. And there's no reason for it. If all you want is access to the underlying T, don't bring smart pointers into the equation. Don't make copies of them. You're just wasting resources for no reason, and you're not expressing yourself clearly. The other reason why I bring this up is, yes, the standard library, shared pointer, protects you from race conditions on, the use count of your resource. But it doesn't protect access to the resource itself. So if you got 2 threads and they're both doing something to a resource T at the same time, that can still cause problems. So you still have to protect your T. It's not going to do that for you. It only protects the smart pointer control block part of the equation. That part is taken care of for you. Now, in the special make shared case here, one thing you might be wondering about is, well, how does it work with a weak pointer? Let's say you've got 1 smart pointer and 1 weak pointer here. So the use count is 1 and the weak count is 2. Then you destroy this smart pointer. So these references go away. The use count becomes 0, the weak count becomes 1, and T should be destroyed. The allocation should be freed. But the control block and T share a single memory allocation, so you can't free that memory without also destroying the control block. So what happens? Well, the answer is the destructor for T is called in place. So the destruction procedure happens, but this memory allocation remains as a little bit of a zombie memory allocation until the control block is freed, and then it all goes away. And you might be thinking, well, that's pretty wasteful. It depends. If T is a vector, it's only going to be like maybe 24 bytes in here. And your 4 megabytes of actual data is in a separate heap allocation that's managed by the vector. So when the use count goes to 0, the destructor for your vector is called. This 4 megabytes will be deallocated, and you'll only be left with the 24 bytes of the actual vector object itself. So usually it's enough just to call the destructor, and then you've got a little bit left over zombie until the weak pointers go away and this whole thing gets destroyed. But I mean, if the actual object itself is very huge, which is a rare case, then it's something you might have to think about, this kind of zombie allocation. But for the vast majority of cases, you're going to want to prefer make shared. But there's still a little bit left in the shared pointer ecosystem. So there are special functions to cast from one shared pointer type to another. So allow me to demonstrate why they are necessary. All right, let's say we got a base class foo. It's got a virtual destructor. And then we have a derived class bar from foo. And then we have a class foo holder, which holds a shared pointer to foo. Now, what you can do in this case, obviously you can construct a foo holder by passing it an instance of the shared pointer to foo by value. That works, and it should be no surprise to anyone. But what's a little more interesting is that you could also create a derived type bar shared pointer and pass it to a function that takes a shared pointer to foo, and it still works. Now logically it makes sense because, from the basic theory of object-oriented programming, we know that bar supports all the interfaces of foo, and so it should be usable in any place where foo is usable. Under the hood, what is happening is that there is a constructor for shared pointer that allows you to convert from a derived type shared pointer to a base type shared pointer. Now if I make another class here, bar holder, that holds a shared pointer to bar, obviously I can create that by passing it a shared pointer to bar. But now let's look at a little interesting scenario. Let's say I've got some kind of polymorphic factory, and it returns shared pointer to the base type, but inside it's creating some kind of derived type. Now if I try to initialize bar holder with the return value of factory, obviously the compiler isn't going to like it because factory declares itself as returning foo. And we know not all foos are bars. So this is invalid here. But let's say we know that the foo that's returned from here, the shared pointer to foo, is actually a shared pointer to bar. If this were just a simple pointer, we could do a static cast, and we could static cast to the bar type, and it would work. But you can't static cast from a shared pointer to foo to a shared pointer to bar. It just doesn't work. Because as far as the C++ compiler is concerned, these are two unrelated classes. Shared pointer to bar and shared pointer to foo, they don't exist in the same inheritance relationship. They're just different instantiations of the same template. So here is where static pointer cast comes into play. So if you use static pointer cast, which is a function, not something part of the C++ language itself, it will do that conversion for you. It will construct a shared pointer to bar from your shared pointer to foo by casting the managed pointer inside. And we see here, no problems once you use the static pointer cast. And there are versions of that for dynamic pointer cast, const, and reinterpret. And they all work as you would expect from just the C++ compiler behavior for those corresponding casts. All right, I've got one more final boy to introduce to you from the shared pointer ecosystem. And he's a very funky boy indeed. Let me hit you with a little hypothetical scenario here. So you got a shared pointer, some type T, was created with make shared. Doesn't matter if it was or not, but for this example it is. And then you've got a raw pointer to type T. Now, for whatever reason, you want to upgrade that raw pointer to a shared pointer to share in this relationship with the other shared pointers. But you don't have any awareness of the shared pointer system. You only have this raw pointer to T. Now, the naive solution would be, it's no problem. I'll just create, std shared pointer. I'll call the constructor. I'll pass it the raw pointer. And I will get my new shared pointer too. Oh, well, let's try that. If we pass this pointer to a shared pointer constructor, it's going to create another control block with a use count and a week count, 1 and 1. And this shared pointer is also going to point to here, or I should say the control block is going to point to here. And then your shared pointer is going to have a pointer to control block and a pointer to T. And it's going to think it has exclusive ownership of T. But then when this one gets destroyed, this gets freed. These pointers here are going to be invalidated and you're going to have a bad day. The moral of the story is that if you have a shared pointer owning some resource, don't try to create another shared pointer from a raw pointer to that resource, because this one is not going to be aware of this one. These two systems are going to not be aware of each other and they're going to create issues. So from this thought experiment, you might expect, okay, well, it's just not possible to upgrade a raw pointer to a shared pointer. But in fact, there is a mechanism to do that for whatever reason. So in the standard library, there is a class, std enable shared from this. And if you inherit from this class, it's a template class, by the way, so you have to template on the derived type. So you got to do foo, public, enable shared from this, templated on foo. These two have to match. If you do this, you will be able to do that thing that I just showed you. So let's create a foo managed by a shared pointer. We'll check the use count. Then we're going to get a raw pointer to the foo. We're going to check the use count again. And it should be 1 and 1. So a step, it's going to be a 1. We get the raw pointer, and it's still a 1. Here comes the magic trick. We're going to take that raw pointer, and we're going to upgrade it to another shared pointer that is tied into the previous shared pointer. And because we've inherited from enable shared from this, we get two member functions, shared from this and weak from this. So let's do shared from this. And then let's use the original pointer to check the use count. So we step, get the raw pointer, get the second shared pointer from the raw pointer. And what is the use count? It is 2. That's the magic trick. And then you could delete this one and it would go down to 1, and you could delete this one and then it would free the resource. So if you inherit from enable shared from this, you will be able to convert just dumb pointers into smart pointers. Now there is one caveat here. The object must have been created initially allocated as a shared pointer managed resource. So if you just allocate it on the stack and then you call shared from this, things aren't going to end well. Do this, shared from this, and yeah, we get an exception, bad weak pointer, and it doesn't work. You may never ever need to use this. You may never have a requirement to reach for this tool, but just in case, I'll let you know it's a thing that exists. All right, now for the homework. And I got a little bit of an interesting one for you guys today. No spoon feeding. I'm going to make you guys work for it. So remember in part 1, I briefly showed you that make shared only works for resources that are allocated with new and freed with delete. So if you have custom resource types, you have a custom deleter, you cannot use make shared. You have to use the constructor unless you use allocate shared and you provide a custom allocator object that knows how to allocate and deallocate the memory for that resource type. So what I want you guys to do is you're going to create just a basic class with an announcing constructor and destructor, and you are going to use shared pointer with local alloc. This is from the Windows API, so you got to include windows.h. But you're not going to call the shared pointer constructor. You're not going to pass in a custom deleter function. What you're going to do is you're going to use allocate shared. So you're going to have to create your own custom allocator that'll work with the local alloc function and its counterpart local free. But I'm not going to spoon feed you any information about how to make the allocator or anything like that. It's all going to be up to your research. After all, this is advanced C++, is it not? So you should be able to do a little bit of legwork for your own. Bust out them Google chops and so on and so forth. And I mean, if you are in the end defeated and you can't work it yourself, you can always peep the solution video and you can see how chili do. But I'm not setting it up all tidy for you. You're going to have to do your legwork on your own, or you're going to have to admit defeat and peek the solution. Either way, I'm going to see you in a couple of days with a solution to this homework problem. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more advanced C++.